All right, today we're going to tackle a really fundamental question in modern engineering. How in the world do you control something when the world itself is pure chaos? We are diving into some amazing research that offers a brand new solution to what's known as the stabilization problem. Let's get right into it. I mean, really think about it for a second. How does a drone manage to hold perfectly still in a sudden gust of wind? Or how does a robot arm perform some super delicate task even if it gets bumped? The whole answer? Well, it lies in mastering the art of control, and believe me, it is one of the trickiest challenges engineers are up against. You know, every advanced system out there is fighting this kind of unseen battle. Let's go back to that drone. It's not just dealing with a simple, steady breeze. No way. It's getting hammered by chaotic, totally unpredictable gusts of wind from every direction. And these are the kinds of forces that can throw it off balance in a heartbeat.
So the goal, always, is perfect stability. But the enemy, and this is how the researchers frame it, are mismatched disturbances. Now this is a really key idea. These are disruptive forces that hit the system in places where its main controls can't directly push back. It's kind of like trying to stop your car from skidding sideways by only using the gas and the brake. You just don't have the right tools for that specific problem. It's incredibly difficult.
For decades, engineers have had a sort of go-to method for dealing with these complex systems. But as we're about to find out, this classic technique has a critical, and you could even say an explosive, flaw. Okay, so the method is called backstepping. And at first glance, it's a very logical process, right? You break down one big, hairy problem into smaller, more manageable chunks. For each little piece, you design what's called a virtual controller, basically a set of instructions. Then, you calculate the derivative of that to figure out the instructions for the next piece. It's like a pilot calculating the exact force needed for one gust of wind and then using that answer to figure out the response for the next one, and on and on.
But here is the massive catch. With every single step you take, the math doesn't just get a little bit harder, it gets exponentially harder. The calculations just spiral out of control, creating what engineers call an explosion of complexity. The system's computer gets so totally bogged down in these repetitive calculations that it just can't keep up with what's happening in the real world.
And look, this isn't just some abstract theoretical problem. The researchers behind this very paper put it pretty bluntly. They said that once you get to a system with just 3 or more layers of complexity, this classic method becomes almost totally impractical. It is simply too much math to handle.
So how do you solve a problem that just keeps exploding? Well, the smart answer is you don't. You sidestep it completely. And that is exactly what this research proposes. A brilliant, two-part innovation that works like a super sophisticated new autopilot for these systems. The first part of this cool new solution is the MFTDO. The easiest way to think about it is as an incredibly advanced weather sensor on our drone. It doesn't just feel the wind, it measures its exact force and direction and predicts what it's going to do next, all within a finite and very, very short amount of time. It basically sees the chaos coming.
The second piece of the puzzle is the CFB, or Command Filtered Backstepping. This is the smart assistant in the duo. So instead of letting the main controller get completely buried in that explosion of complexity, the CFB takes this brilliant mathematical shortcut. It handles all the heavy computational lifting, and that prevents the system from ever getting overwhelmed in the first place.
Let's dig in a little closer on that first piece, the MFTDO. Its entire job is to predict the unexpected, and its secret weapon is a combination of incredible speed and dead-on accuracy. So here's the absolute game changer. Previous methods, they could only ever approximate the disruptive forces, and usually with a bit of a delay. The MFTDO is totally different. It gives a precise estimation of the disturbance. It knows exactly what it's up against, and that allows for a much more accurate and, of course, a much more effective response.
Now let's switch over to the second part, because this is where it all comes together. While the MFTDO is busy identifying the problem, the CFB is busy taming the math. This is the key to avoiding that whole computational explosion we were just talking about.
And this right here is the shortcut. Remember how that old backstepping method made you calculate the derivative at every single step, over and over and over again? Well, the Command filter doesn't do that. It uses this clever tool called a derivator to estimate those derivatives instead. It gives you the information you need without all the crazy repetitive math, stopping that explosion of complexity dead in its tracks. Okay, this all sounds fantastic, in theory, right? But the big question is, does it actually work in practice? So the researchers put their new autopilot to the test.
They used a simulation of a real-world system, an electro-hydraulic servo system. That's the kind of thing used to control really heavy machinery with super high precision.
And wow, this chart tells a powerful story. That red line you see, that's the actual chaotic disturbance hitting the system. The blue line is the MFTDO's prediction of that disturbance. Just look at how perfectly they overlap. The system isn't just reacting anymore, it's predicting the chaos in almost perfect real time. This is the visual proof that the whole theory works.
So, to wrap it all up, the researchers list 4 main contributions. First, they achieved stability in these really complex systems. Second, they completely avoided that dreaded explosion of complexity. Third, they could precisely estimate all kinds of disturbances in a finite amount of time. And finally, their method works on a way wider range of problems than anything that came before it.
Let's just put that in perspective for a second. Let's look at the before picture. The previous methods, well, they really struggled with mismatched disturbances. They suffered from a huge computational load thanks to that explosion of complexity. Their disturbance estimation was slow and just an approximation, which of course led to very limited precision.
But now, with this new breakthrough, it handles mismatched disturbances, no problem. The computational load is totally manageable. The estimation is precise and happens in finite time. And the overall precision? It's high. It is, across the board, a massive leap forward.
So, why does any of this matter? What's the big deal? Well, because this kind of advanced control theory is the invisible engine that's driving our future. It's what's going to let us build more robust robots that can work in crazy, unpredictable environments, more precise manufacturing tools, and ultimately, more intelligent machines that can safely and effectively navigate our very chaotic world.
And that really leaves us with one final incredible thought. When our machines can not only withstand chaos, but perfectly adapt to it in real time, what new possibilities are unlocked? What huge challenges can be finally solved? That's the exciting future this research is helping to build. Thanks for joining me for this explainer.